Okay, thank you for introducing me. Hi, I'm Phoebe, a physics and biology undergraduate from the University of Leeds, UK, and I'm presenting the work I've carried out during a year-long internship that I recently completed in scientific computing, STFC, where we've been working to develop a mesh-based approach to help in protein simulations. This is in partnership with the University of Leeds, as well as our industrial collaborator, EDF, to further the capabilities of biomolecular simulation. This work has been split up into 4 distinct steps, as I've highlighted here. So I'm going to start off with the motivation for the project itself, as well as the objectives of the project, before summarising the steps we've taken to develop this procedure, as well as summarising the work we've carried out and the next steps for the project. So biomolecular simulations are crucial to enhancing our understanding of the highly dynamic environments within biological cells. Molecular dynamics, or MD, is a popular simulation technique which employs Newtonian mechanics and force fields to compute atomic coordinates over short time steps. MD enables scientists to study various biological folding, stability, and conformational change. Now, biosimulations work in conjunction with experimental techniques to relate static structures to functionality. So there are huge databases of data currently available, formed from data obtained both using experimental and modeling techniques. One major contributor to these databases is X-ray crystallography, which is a widely used approach involving crystallizing the protein structures before subjecting them to X-ray beams to form diffraction patterns, which are then used to identify structures. However, due to issues with crystallizing larger proteins, this is largely limited to smaller structures. Cryo-electron microscopy, however, is not. It allows much larger structures to be described by flash freezing proteins to cryogenic temperatures before subjecting them to electron beams to create 3D reconstructions. The images produced using this technique, however, are far beyond the current simulation capabilities of MD. MD is computationally expensive at these larger length and time scales, as this is largely due to the time step needing to be of order of around a femtosecond, even for much longer time scale simulations. And additionally, you need to consider all the interactions between all the possible atom pairs. Therefore, this highlights the need for a new technique. For larger length and time scales, continuum mechanics is instead being proposed for use in a coarse-grained mesh-based approach, computing bulk quantities instead of simulating each protein atom by atom. Fluctuating finite element analysis, or FFEA, is a method primarily developed at the University of Leeds and now Sheffield, UK too, which is a mesh-based approach in place of a particle-based one. Now, just to note here, this is highlighting some of the time scales and length scales we're considering, mainly aiming in that top right-hand box there. So the aim of this project has been to develop a mesh-based procedure to enhance the capabilities of biomolecular simulations. This is part of a wider collaboration with the University of Leeds and Sheffield to create a new biosimulation package, which is a toolkit of algorithms that will be able to help simulate the different protein interactions that occur within cells. This is hoped to unlock access to the wealth of experimental data emerging from new cryo-EM sources, as well as hoping to enhance the predictive power of biosimulation for drug research. So protein-protein interactions are fundamental to cell life. In this project, we've identified 2 main protein interactions that can be simulated using a mesh-based approach. First is sticking, which I've drawn on the top left there, where 2 proteins form a temporary interaction by sticking at an averaged interface, which I've drawn in red here, between the 2 meshes. Now, this is more biologically realistic for cells. However, it might be much harder to compute. The second we've identified is merging, which is actually a permanent interaction, where the proteins form a bridge between the 2 up to a plane equidistant from the 2 meshes there. Now, this is less biologically realistic, but should be easy to compute. And approximately 80% of the mechanisms developed for this procedure should be applicable for sticking too. Therefore, for this project, we focused on merging. Therefore, we've started to develop our own merging procedure, as seen here. It starts off by inputting the meshes to be desired to merge. Then the subsurfaces, so the regions of interaction, are selected, and a plane which acts as the surface for the joining of the two meshes is orientated equidistant from the two meshes. Projections of the subsurface vertices are then computed parallel to the plane normal directly onto the plane. So you form projection footprints, which are then modified to find some shared average footprint there, which is used as the interface for the joining. The protein subsurface vertices are then reprojected onto this shared footprint before extruding the subsurfaces up to the footprint. So you're forming this bridge I was mentioning earlier, building up new cells, before finally joining the meshes so they form one body there. Now, just to note, this is just showing one merge event. However, the application of this software will be used to simulate many merging events simultaneously. So this is just a simplification. We started off by building a sort of preliminary proof of concept code, but then we went on to build the merging procedure in Code Saturn. This is an open source, massively parallel, multi-purpose EDF software, working with CFD. Now, this is to take advantage of its large and highly optimized adaptable structure and many of its pre-existing functionalities. For example, it already has the extrusion and joining procedure, so the final two steps of the merging algorithm, which we implemented into our code. Now, as I mentioned before, we want to consider many merging events simultaneously. Therefore, we need to make sure the data's strong data locality is conserved. So we're making sure that each of the subsurface data is stored within individual structures to help in the organization of things. So the first few steps, generally pivotal to this merging procedure, are the steps up to, but not including the extrusion. So it's the actual selection of the subsurfaces and then the projection and the footprint computation. So this is split up into these 6 steps seen here. And it's drawn down here, where you're selecting the subsurfaces, projecting their vertices onto the plane, computing the shared footprint, and then reprojecting so that the projections are no longer parallel, but you're still conserving a connectivity. So the surfaces are actually selected using cylinders. So we're selecting a circular surface. These cylinders are aligned using the centers of gravities of the two meshes and the midpoint of these two meshes, or the two centers of gravities, sorry. This is used to cut through the boundary mesh, so then you can select the faces and vertices on that. A plane is then orientated, as I said before, equidistant to these two and aligned perpendicular to the cylinders. The initial projections are then computed parallel to the plane normal and the footprint. So this is what's seen on the plane from above. The footprint properties are computed, so including the barycenter and the radius of the footprint itself. Oh, there we go. It's a bit sticky. Okay, so then as I was saying before, we then needed to compute a shared footprint, as the initial footprints are not conformal, but you obviously need a shared one to actually be able to perform the joining in the first place. So this shared footprint has a barycenter as the average of the two initial footprint barycenters. And sorry, I forgot to note this barycenter is actually computed just as an average of all of the vertices on the plane, so it's a centroid essentially. The radius of this average footprint is then taken to be the smallest of the two initial footprint radii, multiplied by some additional predefined factor, which is arbitrary for now, but could be modified to account for the different biological properties of the proteins. The projections are then recomputed to within this shared footprint, such that they're no longer parallel to the plane normal, but scaling is used to ensure connectivity is conserved. Then with this done, the extrusion can be performed. This is to actually use a pre-existing Code Saturn function, CS mesh extrude. And it's done by providing these extrusion settings by filling out a structure with this detailing. So it's essentially the details of the subsurfaces themselves, so the faces and vertices to be extruded. the actual projection path, so the paths down to the plane. I've drawn this parallel just for simplification, but actually you can see here these paths are not going to be parallel in most cases. Then you need to give details on the number of layers you want in your extrusion. So for here, so I've got 4 layers here, and then the distribution of these layers themselves. So here's some example of 2 successful extrusions. The top right is one with 3 ellipsoids and 2 distinct merging events. And then the second is with 2 cubes. So then the final step of the merging procedure is to actually join the 2 extrusions, so it's forming one mesh. Now again, this is using a pre-existing CodeSaturn function, this time csjoint_add, which requires these following settings here. So this is carried out by looping over all of the merge events. Remember, we've got many distinct merging events occurring. Then identifying the boundary faces to be joined on the planes by using a cylinder again to select this circular subsurface. Then this information is added to a join structure and is added to a list of pending joinings, which are then performed at the end of the process in the finalization step using csjoin_all, and then the mesh is updated. So here I've got a result of the joining interface for one merge event. So this is, imagine this is looking down onto the plane, so it's the flat surface. So what's happened here is that some new faces have been added because the initial faces weren't, the initial surfaces were not conformal. So to make it join, new faces have been added. So some of the cells have been turned from prismatic to polyhedral cells. This is a successful join here. Now, with all this developed, the next step was then to parallelize the code. This is ongoing at the moment. So we've currently got these steps working in parallel. We're currently working to convert the computation of the subsurfaces in parallel because the center of gravities at the moment rely on zones in CodeSaturn, but that would not be a parallel process. So we need to rethink how we're computing our centers of gravities. Here I've got a result for the clock time of one merge event, so between 2 ellipsoids, which each have just over 50,000 cells. So the whole mesh is around 100,000 cells here. However, this is taking less than 1/10 of a second, so this is good timing so far. Okay, so now to actually compute the equations across these meshes. So CDO, or a compatible discrete operator scheme, is being used for this, as it's strong within EDF and our expertise are well aligned to this. So a 3D steady state vector valued heat equation has been implemented using the CDO approach. And it's first been tested on a cubic box with 0 Dirichlet boundary conditions in all 3 directions. Now this mesh is actually made of a mix of both tetrahedral and prismatic elements to assess the ability of CDO approach for mixed element meshes, which will be the case for more biological meshes. So this is a solution. These are the solutions here. So it was obtained using CDO method for a tetra-only mesh and a mixed mesh and compared to a reference produced by a finite different code run on a refined homogeneous mesh. Now, as you can see, the CDO solutions are very close to the finite different reference despite using a coarse grid. So this is all good here. So then with that done, the CDO method has been implemented in CodeSaturn and is used to solve the heat equation across the newly created meshes. So I've got here a 6x6x6 case. So this is 216 ellipsoids with 540 distinct merge events. So you've got each of these ellipsoids connecting up. Now you can see here the characteristic properties of the heat equation. So it's hottest in the middle and then it's coolest around the outside, as would be hoped. And you've got the desired flow actually occurring through each of the meshes, so it's showing there's communication here, which is as desired. Now, actually looking at how to improve the algorithm, as I mentioned before, the subsurface we've selected should be circular. However, with some coarser meshes like this, you've got these unwanted kinks that we want to try and smooth out. Therefore, we've worked to sort the perimeter, so we're actually extracting data from the meshes and looking at reducing this angle here. So we're computing the angle and we're changing it. And then the idea is that we want to actually shift the identified outliers to increase the circularity. So coming into more of a shape here. And just to note, this is an image from looking down onto the sort of projection itself. So you've got the 4 layers of extrusion here, and then the actual joined surface. You can see just through mesh there. So you can see how there's some issues with the shaping. It's a bit hard to see, I guess. Okay, just to summarize, this is the work we've done so far. So we've successfully designed and developed a merging procedure, which is hoped to help in the simulation of biological molecules. This has been implemented at Code Saturn, an EDF software used largely for CFD, but it's very much multi-purpose. We've tested our code on up to 216 ellipsoids so far, but we're looking to further these tests. And we've started conversion to parallel. So the next step is to actually complete this parallelization of the code and to start using some real protein meshes, because at the moment we're mainly using ellipsoids, which obviously quite far from what a protein will actually look like, far simpler, far smoother. So we're looking at trying to implement some more complex meshes. Thank you very much. Any questions?